Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So this video today, I want to continue with our series looking at how to implement a linear algebra library in C++. And in the previous video, if you remember, we looked at how we could go about actually using the code that we'd written so far in order to solve a system of linear equations. And we created the QB_LINSOLVE function that allowed us to do that. Now, as part of that, we also saw that there were some systems of equations that we couldn't solve. And the code that we wrote last time actually just gave us nonsensical results in those conditions. As I said in the video then, there are ways that we can go about looking at a system of linear equations before we try to solve it, which can tell us whether or not the system is likely to have a solution, but also can go on to tell us something about that system which might be useful even if we can't actually get to an actual solution. Now, the way we're going to do that is by looking at a measure that's called the matrix rank. It's simply a measure of the number of linearly independent rows or columns in a matrix. So we're going to have a look at how we can calculate that and exactly what it means, and we're going to go on to have a look at how we can implement that in code. So without much further ado, just quickly before I jump into that, I just want to say that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so you don't miss any future videos. I do try and make a video roughly once a week, although that has slipped a bit recently, but that's what I aim for. So if you subscribe and remember to hit the bell icon for notifications, then you don't need to worry about missing anything. Thank you very much. Okay, without much further ado, let's jump to the computer and let's have a look at how we can calculate the matrix rank. So, a good way to understand why some systems of linear equations have solutions and others do not is to visualize them. Now, to do this effectively, we need to limit ourselves to 3 dimensions, or in other words, systems with 3 equations in 3 unknowns. The same principles apply in any number of dimensions, but 3 dimensions is the most intuitive for visualization purposes. Okay, so let's start with a simple coordinate system in 3D space, as shown here, with our x, y, and z axes and the origin in the center. Now, let's consider the system of equations that we first used back in the videos about matrix inverses. I'll put a link in the description below if you want to go and check those out if you haven't seen them already. If you remember, this system had a solution, so it makes sense to start with this so we can see what it looks like geometrically. The first equation was x plus 3y minus z equals 13. Very conveniently for us, this equation actually represents a plane in 3D space, which means that we can plot this equation onto our 3D coordinate system quite easily. If we do that, we get a result that looks like this. Now let's consider the second equation, 4x minus y plus z equals 9. As before, we'll plot that as a plane, and we get this. Immediately we can see that these 2 planes intersect with each other along a line. So now let's bring in the third equation, 2x plus 4y plus 3z equals minus 6, and see how that looks. And what we can see now is that these 3 planes all intersect at just one point in our 3D coordinate system, which we can highlight. If you remember back to the previous videos, we solved this system of equations to give the solution x equals 4, y equals 1, and z equals minus 6. And we can see that when we plot the 3 planes corresponding to the 3 equations, the planes all intersect at the point 4, 1, minus 6. So we can see that the solution to the system of linear equations is simply the point where the 3 planes all intersect. Remember, of course, that we are limiting ourselves to 3 dimensions here just for this example. Now, what about a system that has no solution? In the last video, we saw a system of equations that gave nonsensical results when we tried to solve it. This happened because this system had no solution. But what does that look like geometrically? Let's consider a simpler example from the following 3 equations. In this case, the 3 planes look like this. Let's have a closer look at what is going on. Now, we see that although these 3 planes do all intersect with each other, they never all intersect at the same place in 3D space. This is why this system has no solution, because the 3 planes never intersect at the same place. Let's consider another example of a system that would have no solution. If we have a plane that is parallel to the xy axis, given by the equation z equals 0, it will look like this. Now, if the other 2 planes are similar to this one, such as z equals 1 and z equals minus 1, for example, we get this. In this case, it is obvious that this system of equations will have no solutions. And finally, let's consider one last example, which might look something like this. In this case, the planes all do clearly intersect with each other. But we see that as the planes all intersect along a line, there would be an infinite number of possible solutions to this system of equations. All of this shows us that there are two possible conditions that can produce a system of equations that cannot be solved. Either the system has no solution because the three planes never intersect at the same point in space, or the system has an infinite number of solutions because the planes all intersect along a line. So, how is this all relevant to writing code to solve systems of linear equations? Well, if there was a way that we could test a system first to see if there was a solution, it would be a lot more efficient because it would save us having to go about calculating the solution to all the equations simply to find that we get a nonsensical answer. Also, even if the system is unsolvable, maybe we can determine which of the two conditions I've just mentioned this system would correspond to. Luckily, we can do this by using the matrix rank. Let's have a look at what the matrix rank is and how we can go about computing it. The rank of a matrix is simply an integer number that represents the number of linearly independent rows or columns the matrix has. But what does this actually mean, and how does this relate to solving systems of linear equations? Let's have a look at an example. In this case, we take the A matrix from the first system of equations that we looked at solving. We know that this system has a solution, so this is a good place to start. If we look carefully at the rows of this matrix, we can see that there would be no way that we can form any one of these rows as a linear combination of the other two. What we mean by that is that no single row can be formed by performing elementary row operations, such as multiplying by a number and adding, for example, on the other rows. This is what we mean by all the rows being linearly independent from each other. So, in this case, there are three rows that are linearly independent, so the rank of this matrix would be 3. As the number of rows in the matrix is also 3, we say that this matrix is full rank. We can test whether the matrix is full rank or not by computing the determinant. Indeed, we have already seen this in the previous video on computing the n by n determinant, where we used that result to test whether a matrix would have an inverse or not. If the determinant is non-zero, then we know that the matrix is full rank, and that all of the rows and columns will be linearly independent of each other. In the case of this matrix, if we compute the determinant, we get a value of -55. This is clearly non-zero, and we can be sure that this matrix is full rank. As I said, this was the A matrix from the solvable system of equations that we saw before, and, as we saw then, the three planes represented by this system of equations all intersect at a single point, which corresponds to the solution of the system. Let's have a look at another example. This is a very simple example of a system with no solution. We can immediately see that the first and third rows are the same, so these two rows are clearly not linearly independent. If we compute the determinant of this matrix, we get a value of 0, so we can tell that this matrix is definitely not full rank. This matrix is the A matrix from the second system of equations that we looked at just now, so it is obvious when we look at this system geometrically that it has no solution. And let's look at one last example. In this case, it might not be as obvious as in the previous example, but the rank of this matrix is also only 2. If you look carefully, you can see that row 3 is actually equal to the difference between rows 2 and 1. Therefore, row 3 is not linearly independent of rows 1 and 2. So, we can see how we can intuitively see what the rank of a matrix will be in these simple cases, but how would we go about actually computing the rank? A very convenient result is that the rank of a matrix is simply equal to the number of non-zero rows left after we perform Gaussian elimination. We have covered the process of Gaussian elimination in previous videos, so I won't go over it again here, except to say that we use elementary row operations to convert the given matrix into upper triangular or row echelon form. If we do that for the first example we considered, which represented the solvable system of equations, we get the result shown here. And we can immediately see that this has 3 rows that are non-zero, by which I mean that at least one element in that row is not equal to 0. Therefore, the rank of this matrix is 3, as we saw before. Looking at the third example from before, if we apply Gaussian elimination to this matrix, we get this result. Clearly, row 3 contains only zeros, and so is not non-zero. The other two rows have at least one element each that is not equal to 0, therefore we can see that the rank of this matrix would be 2, as we saw before. But what about the second example that we looked at? Well, if we try to apply Gaussian elimination to this matrix, the process will fail because there is no way that this matrix can be converted into upper triangular or row echelon form. Does that mean that we cannot compute the rank of this matrix? No. There is another way of computing the rank, which is handy for cases such as this, whereby we use the fact that the rank is equal to the dimension of the largest non-zero submatrix with a non-zero determinant. Let's have a look at what that actually means. Recall from the previous videos how we can extract the submatrix for a given element in the matrix. Obviously, in this case, the largest submatrix will be 2 by 2, so we know that the determinant of the original 3 by 3 matrix is equal to 0, then the rank cannot be greater than 2. So, considering the first element, shown here in blue, we extract the elements of the corresponding submatrix as shown in orange. If we compute the determinant of this submatrix, we find that it is equal to 0. Let's repeat that process for the second element, shown here in blue, with the elements of the submatrix shown in orange as before. Now, if we compute the determinant of this submatrix, we get a value of 2. We can actually stop the process here because we know that this is the largest possible submatrix and it has a non-zero determinant, and therefore its dimension, 2, will indicate the rank of the original matrix. Right, so we have seen that there are two possible methods that we can use to compute the rank of a matrix. We will move on to having a look at how we can implement these in code, starting with the simplest method of counting the number of non-zero rows after Gaussian elimination. Okay, so looking at the code that I've created to implement, as I say, the simplest method of computing the matrix rank, I've just gone ahead and modified the QB matrix 2 header file and class that we've been working on so far to incorporate this function. I thought it would be quite good to make it a function that we could simply call on an instance of the matrix class and then get a result back, being of course an integer representing the rank of that matrix, assuming that it is indeed possible to calculate one. One other change that I have made to the code, so this is the code here for the QB matrix 2 class that we've been talking about all along, and I just want to have a look at, there was something that I mentioned in the previous video that I spotted whilst recording that actually I had done or implemented, not incorrectly, but not as good as it could have been, and that was in the function to calculate or to implement, here we are, Gaussian elimination. So this is the function that we talked about before, which converts the matrix into row echelon form. Now the way this was implemented previously, whilst it worked perfectly well and it returned an instance of the QB matrix 2 class containing the result that we wanted, what I didn't spot when I originally wrote it is that it actually modified the internal data of the matrix that we called it on, which is not really the behavior that I wanted. What I was really after was a function that we could call on a matrix and it would simply return the row echelon version of that matrix, leaving the original matrix untouched. So I've made some minor changes to this, and I'll just talk about those very quickly. Really, what I've done, and this is probably not the very best way of doing it, but it does work. So now what we do instead is we make a copy of the matrix data before we start, and we do this because the procedure below will make changes to the stored matrix data. It essentially operates in place. So rather than rewrite the whole algorithm, I've just added a bit of code at the top to make a temporary copy of the matrix data, and then we're going to do the operation to implement Gauss-Jordan, or do the operation to implement Gaussian elimination, and then at the end we're going to copy that temporary data back over the data that we've modified, which means that we will be left with the original matrix untouched at the end. As I say, a little bit untidy, but it does work. So I've simply put this code in here where you create a new pointer to a variable of type t for temp matrix data, and then we simply allocate the memory for that using new and specify. So we create an array essentially of number of rows by number of columns, and then we simply loop over all of the elements and we copy each element from m underscore matrix data into the temp matrix data array, and that's really it. And then just at the end, nothing else is changed. Just at the end here, we have a little bit of extra code now to restore the original matrix data from the copy. So we simply do the same thing in reverse, and we copy temp matrix data, each element, back into m underscore matrix data, and then make sure to delete temp matrix data because we've allocated ourselves using the keyword new, using the new keyword. Okay, and that was all that I did about that. I just thought I'd mention it because we are going to use the Gaussian elimination code to compute the rank, so it is relevant. So this is the new code. It's not very long. This is a function I've done simply called rank, and this will of course return an integer being the rank of the matrix. And the first thing that we need to do is to convert our given matrix into row echelon form. So that's the relevance of what I was just talking about. So we start off, we create a new instance of the QB matrix 2 class of type T called matrix copy, and we set it equal to this.row echelon. Okay, so this will implement the row echelon function on the current matrix and will return the result into matrix copy. Now, the important thing is we need to test whether or not that was successful. We've seen that there are cases where it isn't possible to use Gaussian elimination to reduce the matrix into row echelon or upper triangular form. So the first thing that we're going to do is test whether or not that process has worked. So we use the .isRowEchelon function that we talked about before to test whether we're in row echelon form or not. So if we're not in row echelon form, then we're going to find the largest non-zero submatrix with non-zero determinant, as we've just been talking about. And what I want to do is actually look at how to implement that in the next video, because that's a slightly complicated algorithm, and I think this video is just going to get too long if I talk about that today. So we're going to look at that next week, so we'll leave that blank. What we're going to talk about this week is the condition where converting our matrix into row echelon form does work. And of course, as we've just seen in the slides, in that case what we can do is we can calculate the rank simply by counting the number of non-zero rows after we perform Gaussian elimination. So we initialize a counter here called num non-zero rows and set that to 0. And we're coming down into this part, so converting to row echelon form did work, so we can simply count the number of non-zero rows to get the rank, okay? And then that actually says the same thing. A little bit over keen on my commenting there, but that's better than being under keen, I think. So we set two variables for the number of rows and the number of columns, which we extract from matrix copy, like so. And then we're simply going to loop over each row, and for each row we want to test whether it has at least one non-zero element. So we do a loop for I is equal to 0 up to 1 less than n rows, like so. And then we're going to loop over all of the columns in that row, and we're going to compute the sum of those as we go. So we initialize col sum to 0, and then we use j as our loop variable, loop over all of the columns in that row, and we test if each element at ij in matrix copy is close enough to 0.0. Remember, we talked about the close enough function before. Because we're allowing for the use of double precision floating points, there's not always any point in testing for absolute equality to 0, because there are many times we're going to get so close to it as to effectively be 0 to all sort of practical senses without necessarily actually being equal to it. So we use our close enough function rather than an absolute test for equality. If indeed that is the case, that we have that element is 0, then we increment col sum like so. Okay, and then when we finished looping over all of the yes, apologies, this is testing if we're not close enough to 0, actually, of course. Apologies, you'll see that clearly from the syntax there. So once we finish looping over all of the columns in that row, we have a look to see if col sum is greater than 0. If col sum is greater than 0, then that means that we had at least one element in that row that was not equal to 0. Okay, and in that case we implement num non-zero rows like so. And actually that is everything that we need to do. Then we, at the end of that, after we've looped through every row and every column in every row, we then simply return the number of non-zero rows, because that is equal to the rank of the matrix. And that's it. It's really very, very simple indeed. Let's have a look at how we could actually go about testing this code. Okay, so I've come into the testing code that we've been working on before. This is test_qblinsolve.cpp, and I'm not going to talk about the code that we've implemented before. All I've done is tack onto the end of this the new test code. So this was the code obviously we wrote before for testing our qblinsolve function for solving linear equations. So that's everything that we saw there. What I'm interested in now, though, or wanting to talk about now, is this for testing the computation of the matrix rank. So we set up some very simple tests. We use first of all, with the solvable system that we talked about first, and we test that we can compute the rank of that correctly. The rank, of course, in that case should be equal to 3. And then we're going to test with the unsolvable system that we just saw, the third example from the slides, which of course has a rank of 2. So we do those two simple tests and we check that we get the results that we expect. And then also we just have a look at what the determinant of the unsolvable system is. It should of course be 0 because that system is not full rank. Okay, so now if we go to the terminal window, we can compile that code using g++ -o test code _qb linear solve, and we want to compile test code _qb linear solve.cpp -std equals c++17. Okay, and that runs without errors. And then if we run our test code _qb linear solve, we get this result. So now of course we're only interested in this bit here, testing the computation of matrix rank. So this was the solvable system that we had, the A matrix of that system, which of course had values 1, 3, -1, 4, -1, 1, 2, 4, and 3. And as we expect, that has a rank of 3 because all 3 rows of that matrix are linearly independent. And when it's reduced to row echelon form, it gives this result here, exactly as we would expect. And testing with the unsolvable system we have here, this of course has a rank of 2, and that is indeed the result we get from this. And if we reduce it to row echelon form, we see we get the result here, showing that we only have 2 rows that contain any elements that are not 0. So the third row is all 0. So of course we have a rank of 2, and we calculate the determinant in the case of the unsolvable system, and we get a value of 0, which would of course indicate that the matrix is not full rank. Okay, so that's really everything I wanted to go over today. I know that's just a little bit short, but the explanation of how to implement code to go through the matrix and count or determine the rank by calculating the dimension of the largest non-zero submatrix with a non-zero determinant is a little bit more long-winded, and I just felt that might be better separated into a different video. Anyway, we've had a look at the code that we need now to do the basic, or indeed the simplest form of calculating the matrix rank. Okay, so that's really everything I wanted to talk about today. We've had a look at the most simplest and indeed most efficient way of calculating the matrix rank simply by counting the number of non-zero rows after we've performed Gaussian elimination. As I said, I deliberately kept this video short this week, so in the video next week we'll go on to look at how we can do that using the determinant method that I've already described. Anyway, I really hope you found this video useful and I hope you've enjoyed it. It's been a great deal of pleasure making it. Let me know what you think in the comments below. It's always good to hear from you. And otherwise, thank you very much for watching, and I really look forward to seeing you in the next video. Bye!